All right, good morning. After the keynote, I see there are still people coming in, but I want to get started. Actually, could you do me a favor and can you turn the light on again? I want to ask a quick question. Is that possible? Can we get the light on again? I want to see the audience. Yes. Quick show of hands. Who is here from Poland? Who is here from Austria, where I'm from? Any Austrians in the house? Any Germans? All right. It's helpful. I just want to get started with, we all know the feeling, right? I know it's a tough day. I mean, for the Austrians, it's easier because we never make it to the World Cup anyway, but we look as desperate as you guys. The Germans up there, I don't know what to say. Polish, I'm sorry, but unfortunately, Poland, I think you're playing Colombia on Sunday, is this correct? Yeah, my wife is Colombian. I'm not sure what it's going to be a tough Sunday for me. All right, now what I also really liked today in the morning, the keynote, I don't remember her name, but she got on stage and got us all exercised, and I thought, you know what we do? We just grab the partner next to each other and we try to do this. Right? Get a little physical exercise. So what I want to talk about today is performance challenges in distributed architectures, and I have a couple of examples of my own life, the companies I've worked with, some of our customers, and the stuff that we found. And I also want to introduce you to a concept that I recently learned from Google, Facebook, and some others, how we can avoid introducing performance and architectural issues in distributed architectures completely automated in your CI/CD pipeline. I want to get started with an example that actually happened to us at Dynatrace. And for this, I make the technical thing here. Let me go over here. So in case you have never seen Dynatrace, this is not going to be a product demo, but I want to show you one feature that we've implemented where we really ran into big challenges. One of the monitoring things we do, one of the things we monitor is AWS. All right? So when we monitor AWS, we are pulling in metrics from CloudWatch. That means we're using an external API. Is anybody familiar with AWS? I assume so, right? CloudWatch. So we pull a lot of metrics from CloudWatch, whether it is of your instances, whether it is around your RDS, your DynamoDB. We're pulling a lot of metrics, and it's really cool because AWS provides all of these metrics for us. And we thought, looks pretty cool until people started complaining about one very interesting thing, which is costs, because AWS charges every time you make a call to their API. So here's the first lesson learned from a performance perspective, but performance not only is in terms of response time and how fast it is, but performance also in terms of costs. So let me switch back to my presentation mode here. So the thing that we did, what I just showed you, is we built one of the features I just showed you, the AWS monitoring. We're using CloudWatch as a third-party API. I assume you build your software also using third-party API. Now, in the first iteration of our monitoring solution, we used the so-called single fetch API. So AWS used to only provide an API where we can fetch individual metrics. And for a very small environment that we monitored, where we only pull in metrics from 12 EC2 instances, 1 RDS, 12 DynamoDB tables, we had to make 907 calls to the AWS CloudWatch API. It took a total of 41 seconds. Internally, we consumed 97 threads to try to pull in all this information as efficient as possible. But this is not efficient at all. Right? And unfortunately, we didn't know about this in the beginning. We never thought about that this could be a problem. Fortunately, AWS then recently announced, in case you guys are doing anything with AWS with the APIs, they are now introduced a bulk fetch API. So for the same scenario, we basically reduced the number of round trips to the APIs by factor 9. Also, it's faster internally. This is still something we need to figure out. But the big thing is this is not only more efficient on the communication channel, how often you go back and forth, than the data you're transforming, but it's very especially also the costs. And one thing that I highlighted here on the top right, it sounds very cheap, 0.01 cents per 1,000 API calls. But if you're making a lot of calls, and if you are building a business, and if you're depending on third-party APIs and your business grows, that means your API calls to your third-party vendors also grows. So you want to immediately always figure out if you're using these API calls in the most efficient ways. So this is the first lesson learned. When you're having a distributed architecture and relying on third-party APIs, make sure you're using them in the most efficient way. And most efficient, there's a lot of factors in here. The number of calls, the data transfer, and the costs. The second thing, by the way, the slides will all be shared. I try to put a lot of links to either blog posts or YouTube videos or GitHub repos on these slides. Another lesson that we have learned is when you're moving to a more distributed architecture, it also means that you're growing your dependencies. Especially what the problem with this is that if you have a problem, and you can see, these are just some screenshots from our monitoring tool. This is not a Dynatrace commercial. If you're using New Relic, App Dynamics, whatever is out there, I hope you use some monitoring tools when you do your architecture validation, when you do your performance testing and monitoring. This is the way we present the data, and this is some of the lessons learned. So what we learned, the more you grow, and this is from a customer, Neiman Marcus, a US-based e-commerce store. They're moving towards ECS and running their microservices on ECS. The challenge with breaking a bigger piece into many smaller pieces, and they're all connected with each other, if you don't have a really good strategy on failover, what happens if one component fails, and if you cannot deal correctly with a failing entity, then something like this happens. You have a bad update to one service and it immediately impacts all the other services that are depending on it, and then it has a cascading effect. And this is why it's important, if you guys are designing distributed systems, you always have to keep an eye on the dependencies, right? I mean, this should be nothing new, but you also need to have an eye on how do you deal with failover. What happens if a system fails? Do we cascade the failure all the way to the top, or do we have a failover mechanism where we can deal with an outage? So for instance, yesterday I talked with an insurance company or with a pharmacy, and they said if people in the US go to a pharmacy and they want to get a diabetic treatment, and let's for instance say they need to pay, and for whatever reason the credit card transaction doesn't work, maybe because of Visa or MasterCard, whoever in the backend is currently down. Do you want to deny that person that stands on the counter and needs their insulin? Do you want to deny them their insulin? Or you build something in a system where you say, well, based on our data, we know that sometimes we have hiccups with our backend system when we make calls to a third-party API. So instead of denying that person the medication that they need, we give them the medication and we figure out a way how to later on process these calls to the next system. Because if you deny them the insulin and they die, you don't want to be in the news, obviously, right? So there's a lot of things we need to think about when we build distributed systems. I tried to come up with a couple of anti-patterns, even though I'm not sure if the word anti-pattern is actually a really good name, but I just chose it. There's a couple of things we constantly see when we analyze distributed applications. Most of them should be familiar. Most of them, if you have been in software engineering for a while, and I don't see all the faces here, so I don't know how old you are, but these are not all of them are new. I may start with the N+1 call pattern. Classical monolithic code, very easy, very pseudo, very basic, right? Iterating through a list of products to get the overall product value, or the total sum. Works well within one process. If you distribute this in a distributed system where product get value, for instance, makes a call to now a microservice because this is so cool, then we may end up with a big problem. So here is actually one of our customers that had quota service, so it's an insurance company, and they thought they are extracting their monolithic code base into smaller services. So now every time they make, or a customer is requesting a quote, they're making 44 calls to product services, because the initial monolithic code that was iterating through a loop and going through each individual item in their insurance policy, making in the old days local calls, are now making distributed calls. That means you always have the marshalling, you have the overhead of transferring this data over the wire, so you basically end up potentially with a lot of calls, and you initially never thought about it. if you never did the end-to-end analysis, okay? So if you're doing especially a monolith to microservice migration project, always make sure that whatever you end up with still makes sense. Or if you have too fine-grained services and you have too many round trips, like what we had earlier with AWS when I started my presentation. AWS also realized that, and they built a better API to support some of these use cases. Another example, LandBay. LandBay is a financial institution in the UK. This is their architecture on AWS. You can see all the different services that they use. ECS for the web tier. They're using microservice also on ECS in the back end, and so on. RDS as a data store. Beautiful diagram. Now, same thing what they realized is when they have, now from the left to the right, a message coming in onto a system, one message translates into 74 entries that are being pushed into the database, 24 messages put into a queue. Then there's different listeners. Different listeners take either all the 24 or just 22 out of the queue. The rest of them, of the 2 that are missing here, are taken out by yet another listener, and then it's propagated through the system, where you see that a single message, a single transaction is now kind of spreading through an environment, spreading through the system, and it doesn't stop here. It really goes on X, Y, and Z, so there's many, many more layers in the back, many more services that are called. What I want to tell you again is it always looks cool from the outside if you're breaking things into smaller pieces, and it obviously makes sense, but you always have to reevaluate how 2 services are communicating with each other. Okay, what did we define the right API? What are the use cases? Maybe over the time, the consumer of a service, they have changed their pattern, and now maybe they require a more bulky version of your API. So always reevaluate, because processing one single transaction that is making 243 individual hops on just the front end of the system seems a little excessive. Because remember, you also have to pay for all of this. Yes, this all runs in Amazon. They don't have the physical hardware, but somebody has to pay for all of this. So this is the N+1 call pattern. That means one call spreads out into multiples. N+1 query pattern. This is a classical one from the traditional, let's say, 3-tier architecture where you have, let's say, a monolithic app that calls multiple times to the database. Similar here, coming back from the quote example, right? One quote initially, one call comes in here, 87 calls to the database. And this is also because of inefficiency on how they access the database. They were using Hibernate, which is obviously a great ER tool, but it's once used wrongly, not optimized for the use cases, you end up with a lot of duplicated calls to the database, and especially if you're breaking up a monolith that used to use the database efficiently, and now you're breaking it into smaller pieces, and all of these individual pieces now need to fetch the same type of data. So this is why if you're breaking things apart, if you're building distributed system, be smart and analyze who is needing what type of data, and can we optimize this a little bit. Another pattern is payload flood. What you see here is, again, it's a document management system. So what they did, they said we have a document that comes in initially, and then we are sending that, we do the initial processing, we're transforming the document, we sign it, and then we ship it. This was kind of what they call the transaction flow through different Tomcats in this case. What was interesting when they analyzed how much data is actually transferred, so what we analyzed then is the number of bytes being sent between the individual tiers. We realized when they sent in a 10 megabyte initial document, the 10 megabyte document after processing is 18 megabytes, it becomes 20 megabytes, and then it becomes 21 at the very end. And the whole document is always sent between the individual services, even though each individual service just does one little piece and only needs a little piece of the whole document. But this is obviously something, it works, but if you have to worry about the network, and if you have to provide the network capacity, this is going to be very bad in the end. So what they have came up with is a solution that is slightly better at least. So the initial document comes in, it gets processed initially, then only those pieces that need to be transformed are sent to the transformation servers. Only those pieces that need to be signed are getting sent to the sign service, and in the end the full document is then sent over to the shipping service. right? Still looks excessive, but it's already more than a 50% improvement in terms of the bytes that are sent over the network. Now, all these use cases, remember, what I want to show you here, because when we talked with these developers and architects, they never thought about looking at these numbers. And I'm not sure if you guys are looking at these numbers. If you do, that's great. If this is new for you, hey, network, we actually send stuff over. What data do we send over where? Does it really need to be sent there? Granularity. Another great example where we have, as you can see, it's the same customer here. They came up with the idea that for encryption purposes, instead of having the encryption in every single service, they wanted to extract it into a separate microservice so that they can call it. So now what happens for the one document that comes in, they make the calls to the individual steps, but every service makes multiple calls to the encryption service to encrypt individual pieces of data, encrypt or decrypt. So now for a single document, they end up with 316 calls to that new encryption service, which means, again, this potentially lives on a different part of the infrastructure. You need to send data over. This is very costly and very inefficient. So that's why if you're breaking things apart, you want to figure out what is smart to break out as a separate service and what is better to be left close to where you need it. Tight coupling. As you can see here, this is a classical monolith, right? I always use this as an example of, on the left side, we have our Apache front end, and this is a big monolith that we want to break apart. Maybe it runs in a web sphere, maybe it runs in some other application container. By the way, quick show of hands, who is currently dealing with monoliths and you have a project where you need to break the monolith apart? Yeah, and who is successful? One hand. That's good, I want to talk with you. So what we have been seeing and what we've been advocating for is, if you have a monolithic code base, then obviously we think, if we have done our job right over the years, we have actually a well-structured monolith. That means the code base within the big monolith, you have certain modules, you have certain classes, you have certain components, and theoretically, your monolith internally looks like this. You have a journey service, you have a booking service, you have a configuration, a check destination. And you want to break this apart. Now, the question though is, shall we just break it apart? Shall we invest days, weeks, or months to really refactor and break individual pieces out? Or shall we first have a look at how are these individual components and classes and services within our monolithic code base calling each other right now? Because right now, and I need a victim now in the first row. What's your name in the first row? Adam, right? Adam, if you are the architect and you tell me, Andy, I believe I know the code base so well and I want to extract journey service from check destination, then I tell you maybe not, because we currently have a one-to-one relationship. Every time you call the journey service component, that part of the code base, it always calls into check destination. So ripping this apart doesn't probably make sense. So what we do here, and there's great tools out there that can give you all this information, right? Before you start a refactoring project, please just don't do it based on your gut feeling. Adam, even though I know you are obviously, you know a lot of stuff, but always validate first with tools. Because don't break something apart and then realize later that this was not a good idea. Because then you realize that you have a lot of calls going back and forth. All right. Inefficient service flow. I've been doing a lot of work recently, a couple of years ago, around web performance optimization. And when I now look at server-side architectures, distributed architectures, then I see some familiar things where I just see either too many things being loaded, nothing is cached, too many round trips, not bringing data close to the end user. So what you see here is, again, what we call a transaction flow or a service flow with all the dependencies. We've seen pictures from that before. The most important thing for me is making sure that you always keep an eye on what happens end to end. What happens end to end in your applications. And not just looking at what happens within an hour. I worked with a bank recently, and they are currently breaking they have a mainframe in the backend, they have a Java middleware, and they're now building new Spring Boot apps that they run in OpenShift. and they want to break this middleware, this Java monolithic container, or this Java monolith into smaller pieces, and then push it over to OpenShift. And what they are doing, they're saying, we're not doing this like this. We don't look at breaking the monolith. We first analyze what are the key features of our banking software. People can log in, they can look at their accounts, they can make a transaction, they can buy stocks. So they always analyze end-to-end flows from their individual business features, and then figure out, so now how can we optimize this, and what should the picture look like? And they always keep an eye on that it doesn't become too complicated, because this doesn't look really complicated, but if you don't keep an eye on it, can become very complicated, as you can see here. Right? This is what I call this is the great prototype that works well in testing, and this is then in production. And you laugh, but the reason why this is because in production, obviously, you deal with other systems. You may have other configurations. Somebody may forgot some certain configuration because they don't do configuration as code that well. You all of a sudden have other people in the organization that also make changes to certain environments and configurations and have to deal with this. And then you end up with a big mess. And then you end up with a lot of these classical patterns. Right? Individual service calling other services either recursively, the classical n+1 pattern that I said earlier, no caching layer, every call always goes all the way through, even though there's certain data that only gets updated once a day or once a week. So why always go back to the database and not cache it somewhere else, especially reporting data? So keep an eye on that something that starts like this, if you do a distributed architecture, in build number 1, or let's say in sprint number 1, doesn't end up like this in sprint 2, 3, and 4. Always constantly have an eye on this. What I say here, and this is a concept that I want to explain later on, if these are individual microservices, and Adam, I have to come to you again, right? Adam, if you're responsible for one of these services, then you sit down with your architect and with your team leads, and then you say, I'm writing this service, and I think the service should only be called, let's say, by somebody in the front, and I'm only going to call a certain backend service. Never should this service call anything else. So you can actually define the dependencies. And what you should do, you should make sure to enforce these dependencies for every single code check-in. So when you're pushing code changes through the pipeline, through a delivery pipeline, and you run your tests, the stuff that you discussed with your architect, one call can come in from this service, and I may be able to make one call out. You can always validate dynamically if this is still the case. And if what's the gentleman's name beside you? Piotr. If you're on his team and you make a code change because he's on vacation, and you introduce a new library, and all of a sudden, instead of having one call to the database, you make another call to a new microservice. If you validate these dependencies automatically in the pipeline, because you analyze the dynamic flow of your tests, then you can say, oh my God, Adam is not here. He defined in the beginning, I am only allowed to make one call. Now my pipeline fails because I did something that now makes 2 calls. So I probably need to double check with Adam when he comes back. Because if you don't do it, right, you start from here, and then you end up here after Adam is back from vacation. And that's not what we want. So this is the concept of monitoring as code. This is something I learned from Google, and I'll show you later how this can be implemented in the pipeline for real. Just some examples. The classical cascading effect of services that are calling each other recursively. Right? This list goes on and on and on and on. Right? Not very efficient, the same microservice. And I know this is very small, but there's also, remember, if you look at the slides later on, there's going to be either links on the slides or in the slide notes to additional articles or YouTube videos or GitHub repositories. But this is a very classical example where the same service is called all over recursively, and every time the service, all of these blue lines here, actually, sorry, the orange lines, these are database calls. So the service is calling itself recursively, and every time it's called, it's querying the same data all over. Dependencies. I talked about dependencies a lot. This is an example of another insurance company. It looks really easy. There's an end user that is accessing their client center from the web, and then there's a range of front-end servers. But it's just the tip of the iceberg, because this is really what they have. Right? This is the architecture. Adam, how long were you on vacation to let this happen? So I know we often, and I'm sure there's people in here and you have maybe there's some of you that have very small teams, but you may work in a large organization and you have different teams that are working on the whole big product, right? And you typically, if you work in a big organization, you only see your little piece of the puzzle. I do hope, though, that somebody keeps an eye on the big picture, because this is, first of all, very hard to maintain, very hard to understand. So a lot of potential here for problems, both architecturally, performance, scalability, costs, right? If you have all these duplicated calls. So this is a challenge. So that's why what we are advocating for is always look at, Adam, if you are, that's the bad thing if you sit in the first row. If you are responsible for a service, you always want to ask yourself, who is actually depending on me? Who is using me? And I want to validate this in my test environment when I run my tests, but also maybe in a production environment. And therefore, again, use tools that can actually give you the full chain of events, the full stack trace. So the reverse, we call this the back trace in our product. So you can focus on a service like the journey service, and you can see that there were 5,610 calls coming in, and you can see where these calls came in. So it's a reverse stack trace, but not just within one JVM, but across your complete end-to-end architecture. And then you can see that most of these calls are they're all going, the call is basically forwarded, because this 5,600 originated from 5,100 on the Nginx front end, which was called by this guy, and so on and so forth. So very important to always understand, who am I depending on? Not only for you to know, but if you are planning changes, right? And then you're going on vacation, and then Piotr, you're jumping in again, and then you make a change to his journey service, then you want to talk with the people that are potentially depending on your changes, right? If you break something, these people they're all going to cry. What happened? Right? So be careful, and make sure you're aware of everything that happens. All right. So recap a couple of things. I know some of them may sound very basic, but the reason why I bring it up is because we see this on a day-to-day basis. Most of these examples came in the last couple of months. And even though we've been talking about the N+1 query pattern probably before I was even born, right? I guess so. So these are all the patterns. Have a look at it again later on in my slides. Now here's what I want to now tell you, how we can automate all of these checks in CI/CD. I'm proposing to you something now that I call monitoring as code. And the same, I've double-checked this and validated this with the head of SRE at Google. And I happened to run into him into Acacio Cruz a couple of weeks ago at a conference. And he also told me how they do it at Google. And I want to show you what they do, and also how I think we can all do it. So the idea is, again, what I showed you earlier. If this is build 17, that's great. If this is build 21, then we have a problem. Because we have all of these things that crawled into our architecture. So we need to constantly validate the dependencies. What we also need to do, we need to constantly validate before and after performance on the individual patterns or on your individual service endpoints. So what I said earlier from Google, what I learned, and I really highly recommend Acacio Cruz. So he currently works for Google in Switzerland, in Zurich, in their office, and he gives a lot of great talks. There's one here that he gave at Dev1 in April, how Google is doing load shedding and how Google is dealing with distributed architectures and how it actually looks like. And I also got him on a little podcast, which would be, in case you want to listen into it. What is interesting, what he told me, every time when they are building services, they basically tag the service. Every service has a particular type. So I can build a front-end service, I can build a back-end service, I can build a middleware service, but depending on the type, it is automatically defined what my service is allowed to do and who is allowed to use my service. So for instance, a front-end service is never allowed to go directly to the database. A database can only be accessed by a back-end service. And this is now automatically enforced in their CI/CD. So that means if they're pushing a service through the pipeline and it is tagged as it is a front-end service, the pipeline fails in case the front-end service makes a call to a database. because that's not what it's supposed to do. Yeah. So the way I came up with it is, and whether you use JSON, YAML, or however you do it, I came up with a concept that is called monitoring as code, even though it should probably be a little broader. It should be architecture validation as code, or quality as code might be even a broader term. But what I've done here, I have, I advocate, and let me just switch back quickly to my environment. Let me switch back here. And actually, let me kick off another build. So what I'm going to show you now is actually a tutorial that is online. I built it's a Node.js based microservice. I could have also used a Java service, but I used Node.js, and I put everything out on GitHub. So in case you want to do this, it's called the AWS DevOps tutorial. Okay, so this is all the code is out there. The source code of the app, the CloudFormation template that creates the pipeline and everything. And you can do it all with the AWS free tier, and you can also do it if you want to use Dynatrace for monitoring with the free trial of Dynatrace. So I want to just kick off a new build, because I just uploaded before I get started a new build of my microservice. So what will happen? Hopefully, I check out my source code. I have my app, I have my tests, and I have what I call monspec. And then, before I show you monspec, then it goes on. There's a staging, so I deploy the version in staging. That means I have EC2 instances dedicated for staging and for production. Then I deploy my tests. And then I have a step in here that is called validate my build. So that means I deploy, and then I call a Lambda function that is looking at the deployed version that is currently under test, because I immediately run the tests. And this Lambda function is then actually looking at this particular monspec file. And here is the monspec file. So what is monspec? Monspec allows you to say, hey, Lambda function in my case, or it could be a Python script. I also wrote a Python library that is doing the same thing. I basically say every time when I'm pushing my service through. So first of all, what is my service? My service, and I'm coming back to Adam. Adam, you're writing, is this big enough? Yeah. So I'm writing a service, and it's not dev team A, it's dev team Adam. Here we go. Perfect. And my service will be deployed in a staging environment and in a production environment. So you can define what type of environments your service will be deployed. We also can specify how my service is tagged in the individual environments. So we are using a combination of AWS tags, of container tags. So we can define how my pipeline is deploying my service, and how then my monitoring tool, in this case Dynatrace, is detecting it. And then I can say, I want to validate certain metrics. So for instance, I want to validate response time, right? I want to make sure that the response time is not getting worse from build to build. Or failure rate. More importantly are these things here. Two relationships. So how many calls do I make to the next level in line? I can either avoid the limit here, so I can remove this, and then my Lambda function is just comparing it with the previous build, or with what happens in production. I can define with what I want to compare it. Or, Adam, if we two sit down and you say, my service is only allowed to call these two other services, then you can specify this here. So we define our contract, basically. Also, from relationships runs on, we can say on how many nodes my service is running on. That means if I'm pushing it through my pipeline and I'm running load against it, I'm simulating thousands of users, then I want to say, does ECS or Fargate scale it up to 1 node, 5 nodes, 10 nodes? How many nodes do we have? And how does this change from build to build? So how does this really look like? Let me see. It's still deploying. So my app is deploying in the backend. I just show you here. So this is my staging environment. This is my Linux machine now that is tagged with staging. And here is my service that is monitored. Here is my tag. Right, this is the staging tag. So this is how I actually can, from the pipeline, call to the monitoring tool and say, hey, monitoring tool, I want you to tell me what is the current response time of that service, what's the failure rate, on how many nodes does it run, 1, 2, did it already scale up, and to how many other services does it call. So this is all dependency information that we automatically get. So here we go, right? This is the dependency information. It seems my Node.js, my sample Node.js in staging calls some external services, and that's here. And my pipeline is automatically validating this. So if I go back to my pipeline, it will take about 5 minutes. It's currently in the approval stage, and I don't want to wait. I've configured it to wait at least 5 minutes. So my Lambda function will actually only do the work after 5 minutes because I want to make sure that I have properly run some load tests against it. But this is basically, let me just refresh the screen. This is now my output. So every time I run my Adam, every time when we run a pipeline, every row here, every column represents a build. I ran 1, 2, 3, 4 builds already. And then every time I have a build, my Lambda function in this case is pulling in all these metrics. Average response time, 90th percentile, failure rate, service request, this is the load, and then here are the relationships, from relationships and runs on. So we're basically monitoring this, and I get an overview from build to build to build. And if Piotr, if you come in and you make a code change and you run the pipeline, and all of a sudden you introduce a new dependency, then one of these numbers will go up, and it will automatically stop the pipeline. Okay, so this is one way I propose to do it with my monspec file, as I call it, my JSON file. This is just a guidance from me, but you can obviously feel free to do it however you want. It also depends obviously on what type of data you get out of your monitoring system, out of your pipeline. But what I want to advocate for is that you want to make sure that you avoid this situation. You want to avoid that you start with this and then you go on vacation and then you come back after 2 weeks and you end up with something like this because your pipeline did not enforce your basic architectural rules. Does this make sense? Yeah. Awesome. So that means we can now all go on vacation after we implemented it and we make sure that all of our colleagues are doing their job right. Cool. All right, what else do we have here? I think I already kind of spearheaded over, I explained what my pipeline is doing. So the initial pipeline that I built, and if you want to go through it, this is again the link, right? So I have my build that I'm deploying. In my case, I'm using code deploy and deploy it on an EC2 instance. Then in the traditional sense, if you're creating an AWS code pipeline or if you're using any of the other pipeline tools, in code pipeline you can run your tests, but then typically you have obviously the manual approval, which I hate. I don't like manual. That's why I wrote also this Lambda function that is actually figuring out if enough data is there and if we are meeting our specifications and then automatically approving it. But this is kind of the old way. If somebody approves it, we deploy it into production. If we approve production, we want to obviously make sure, right, looking at any of the monitoring tools. There's a lot of, I know this list is by far not complete. I'm sure there's other monitoring vendors out there as well, and they all provide you similar metrics. When you deploy into production or when you do a blue-green deployment, again, validate how the production deployment works, and then in the end, hopefully your users are happy. Then we can wait for the next game from Poland, and they win, and we get terribly drunk. Unfortunately, maybe not all of your users get drunk, but maybe they get angry in case you deployed something in production that didn't work, and then you are in the bar, and you don't want to sit there manually, but sometimes you have to kick in and then do a manual rollback or whatever you do. So the problem that I have with this, as I explained, right, this is the pipeline I started with, but the problem that I have is manual, 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 and that's why I came up with this concept of the monspec file. Because what I'm doing here, when I run my tests, my performance tests, I typically open up dashboards and I look at response time, failure rate, CPU consumption, memory, all that stuff, and I compare it with the previous build. But this is boring and manual. That's why if I write it down into my file, I can fully automatically validate these metrics by comparing different time frames or different builds. What I can also do, this is also what Google is doing. Google is even, when I switch back to my monspec file, Google goes a step further. They say, we actually know what type of endpoints my service provides. And I can even specify which metrics I want to validate per endpoint and what the proposed value should be. What Google even does, they are generating the tests based on this file. Because Adam, if we sit down and say this is a service, the service is providing these 5 endpoints, and it's allowed to be called from the front end, and it's allowed to call the backend database, we can generate the tests based on this specification. We can look into production data to figure out the workload distribution, so which API is called how often in the real life, so that we don't just randomly guess. Then we run our tests in the pipeline, and then we validate how many calls are really coming in, how many calls are going out. And then if we do all this, we have a beautiful pipeline that is much better than before, because now, every time we deploy, we are telling our system, in this case our monitoring tool, what we are deploying, but more importantly, the approval part. The approval part is where I wrote a Lambda function, or it can be anything, and it basically goes off and pulls in all these metrics that Adam and I defined, and then it compares it, and then says good or no good. And I can do this for my staging environment, and I can also do it for production. Right? In production, I may look at other metrics. I may look at are people still able to access the site? Do we still have people that can go through the checkout process? Do we still have people that buy stuff? And then the last step that I'm also advocating for, and this is especially, I think, better and easier possible with distributed apps and smaller services, in case we deploy it all the way in prod, and we monitor it, and everything is happy, then we can go for a beer, as I said earlier, because we have to celebrate from time to time. But if something happens, and this is again true, this is what all the monitoring tools give you. The monitoring tools will tell you in case there is actually a problem. And then they do not only send you an email that you ignore anyway, because it ends up in a spam folder somewhere, but you can actually call other tools. For instance, we can call another Lambda function. We can call an Ansible Tower script. We can call whatever you want that is then triggering, for instance, an automated rollback, or whatever you would do to fix the problem. So this is something we are advocating for as well. Again, this is all on GitHub. It is using, let's say, a simple microservice, but I think it gets the point across what I wanted to make, which is constantly look at these key things that we have seen all over. Too many calls coming into a service, too many dependencies, sending too much data over the wire, and all of this kind of comes in from code change to code change because nobody constantly keeps an eye on it. That's why I hope you are trying to figure out how to automate all these checks in your pipeline as well. All right, I think that's it from my side. I know we have about 6 minutes or 7 minutes left based on my clock. I'm doing another talk later this afternoon where I actually explain how we, within our company, use all this, and it's not always as easy as just showing some slides. I also talk about the dark sides. But yeah, if there's questions, I'm not sure if we have a microphone or just come up on stage later on. But does anybody have a question right now? Yeah. Shout it out loud. So you said normally it doesn't make sense to do any performance test outside of prod. I disagree completely. So because you can test the performance characteristics not only of your whole system, but also parts of your system, parts of your services that you have. So what we, for instance, internally have, and this is what I'm going to talk about in the afternoon, we have a continuous performance environment, which is an environment that is not a complete replica, but a partial replica of our production environment that is constantly under load, 24/7, where we always simulate load that is from the workload perspective, similar to what we see in production. And what we do, every build gets automatically deployed into that environment that is constantly under load. The first thing we test is how does a deployment actually work on a system that is there's always under load, because in production that's the same thing. Eventually, when we deploy into production, we are going to deploy in an environment that is under load. Right? So it's the first thing we validate. The second thing we validate, we let the tests, we deploy, and then we look constantly at the numbers as they come in with the new build, and then we automatically validate, did the behavior change to the previous build? Now we do this for a small section of our product, for certain services. We do it for certain, in an integration environment, and then obviously in production, we do it on the production environment. But where I say that disagree is because we do a lot of performance testing on individual services, where we set them under load and we want to figure out, did the code change the memory behavior? Did the code change the behavior of how many calls come in and come out? How many bytes are transferred? Did the configuration change to the JVM memory settings, for instance, change the garbage collection behavior? And you can also test this on small environments. Much faster because you don't need the whole environment. And the reason why you want to do it faster is because you want to give developers faster feedback. So you said I didn't get it. Well, we still do end-to-end tests and all of that. But what I'm saying is, if you have individual services, we also do performance tests on these individual services, because we want a regression is not just I open up that, I run this Selenium script and I cannot click on that button. A regression is also we are consuming 20% more memory than before, because then somebody needs to say, why do we need 20% more memory? Do we add feature that justifies it, or did we update a third-party library that has a memory leak, for instance? That's why it is a combination, right? We still run our unit tests, we still run our integration tests and functional tests as well. But what I'm also saying is we also run load tests within our CI environment, okay, on smaller components of our software, not only the end-to-end full deployed system. All right, I think people, anybody else? Yeah.
Actually, proceeding with the previous question, usually it makes sense to do perf tests with the data as much similar to production.
Exactly. Yeah.
But you can't just put production DB and use it.
Yeah.
How do you do it?
So the question is, it's obviously the best if you can do your load test with production-like data, but obviously you cannot use the production data. And how do we do it? So you can obviously duplicate data if that's possible. There's data generators out there. What I have one example in the afternoon. Mark Tomlinson, he's the performance engineer at PayPal, and what they are doing, they are constantly taking snapshots of the production database, but then he called it Swiss cheesing, because this is financial data, so there's a lot of confidential stuff in there. So they basically have a transformation process where they are then manipulating data that should not be seen by anybody outside, right? But they are constantly generating basically a production replica, or at least from the volume and from the semantics of the data.
Yeah, I was more the question is more how exactly the guy you described.
Yeah.
No,
Mark Tomlinson is one of my friends. He works at PayPal, but he has a lot of talks out there where he talks about how to correctly how to generate production-like data. Okay, so just Google it, Mark Tomlinson. Okay, very good guy. Yeah. How often do we see these automated performance tests failing? It depends on how often you run these automated performance tests. So within our company, we run them 24/7, and since we've changed to constantly on, and every build, or let's say every daily build, every nightly build gets deployed into this continuous performance environment, the performance regressions went down because the changes are smaller, and also our engineers throughout the day get some performance feedback throughout from their CI environment. Right? So that means if I'm making a code change, after a couple of minutes, I get feedback on whether I've introduced any new n+1 query pattern, if I've increased my memory footprint, if I've increased something like this. So I can fix this right away before my code change then goes into the nightly build that then goes into the full performance environment. I would say it happens quite frequently. Yeah. I give you another link this afternoon. So I'm doing another talk, and our chief performance architect, Thomas Steinmaurer, 2 weeks ago, he did a session with Neotis. They had a virtual conference, and all the videos are now online. And he actually talked about how our continuous performance validation works. And so Thomas Steinmaurer, Thomas and then Steinmaurer. If you Google for him, you will find his talk. It's about continuous performance validation, as he calls it. And he also gives all the statistics on how much load we are simulating, how often we run, and how many tests we find. I can tweet it, yeah? Yeah. Actually, I think I tweeted it yesterday. So just look at my feed, because it was just published yesterday, the recording. All right. Flaky results, yeah. How do we handle flaky results? Is that the question? Yeah. So we do for these environments, the large-scale performance environments, we constantly test our hardware that we run on. And to be quite honestly, we are running most of our tests using configuration as code on AWS. So it's the same is true for production and pre-prod. So we are using the same hardware configuration. We also do some performance testing with our unit tests. So we analyze how fast are our unit tests and our integration tests. There's also a blog post that Stefan Frandl wrote. We are calibrating our test environment. That means when we are running our unit tests, we typically do a couple of warm-up runs to make sure we are calibrating. We have no side effects of something else running, or maybe a JVM not being warmed up enough. He wrote a nice article. So Stefan Frandl, I can also tweet it, and he talks about how we are calibrating our test environment. Yeah. So, but for pure performance tests, that's not that big of an issue, because we are really using beefy hardware and similar hardware configuration than in production. But for these unit and integration tests that we run, where we also look at things like execution time, this can be very flaky, because the faster they run, the more flakiness you get. And we have a concept on that. Yeah.
What about caching in performance tests? Because you cache something, it might send you five cores somewhere, so you don't see it, so you run them without caching, or?
Yeah, we test all different types of combinations. So we have tests where we basically say this is as the system starts up, where the caches are empty. So we run these tests as startup tests. Most of our tests, though, focus now on caches that are typically primed and full.
So you basically always start the new boxes with the caches. You don't share them between the tests.
Exactly. We keep, so for our continuous performance environment, this is constantly under load. Because what we do as Dynatrace, we offer our software as a SaaS, right? Every 2 weeks, we deploy a new build. And we deploy that build on several thousand nodes out there in EC2 to our customers, live, right? And so that's why also our continuous performance environment is mimicking this environment, constantly under load, and then we test the deployment. But we also have to test the other use case, because sometimes we have to bring up new cluster nodes or completely new regions in AWS where there's no caches primed. That's why we also test this particular situation. How does the system behave? For instance, we have a promotion in Singapore, right? And then we need to bring up a lot of new clusters. We want to make sure that the user experience is also good there when we just bring something up. But the main tests, though, focus on a system that is constantly under load. All right, I think I am a little out of time. If you can find me, we also have a booth up there. I'll try to stick around at the booth on the second floor, I believe. And if there's more questions, you can find me on Twitter as well. And my email is my first name dot last name @dynatrace.com if you want to follow up. Thank you.